Greetings everyone, my name is Rukumar Vyas from Semester 3 pursuing BTech in Information and Communication Technology ICT at Marwadi University. This conceptualization video is my submission for the active learning assignment in the subject Introduction to Communication Engineering. In this video we'll be exploring transmission impairment. We'll be particularly looking at noise, attenuation and distortion. Transmission impairments. Let us first understand what are transmission impairments. In any communication system, data is sent from the transmitter to the receiver in the form of signals, which are nothing but variation in any electrical quantity, via a communication channel. These communication channels are not perfect. All the communication channels that exist in the world have some or the other imperfections. While doing theoretical study and calculation, we can assume a channel to be perfect without any imperfections. But this is ideal case. All the real world communication channels have imperfections to some extent. Some are very imperfect, while other communication channels have small imperfections, but they are there. Now these imperfections affect our signal negatively and generate faults and errors, and they also create alterations in our original signal. This means that the signal at the beginning of the medium is not the same as the signal at the receiving end. Therefore, what is sent is not what is received. And we don't want that. This is undesirable. The whole gist of communication is that whatever we are sending must be received at the receiving end without any alterations or errors. This phenomena is known as transmission impairment. There are three main causes of transmission impairment, which are attenuation, noise, and distortion. Let us first discuss attenuation. Attenuation means loss of energy. All the communication channels that exist impart some amount of resistance to the passage of the signal. Thus, when a signal, simple or composite, travels through a medium, it loses some of its energy in overcoming the resistances of the medium. And this is why a wire carrying an electrical signal gets warm, if not hot, after a while, because some of the electrical energy in the signal is converted to heat. And to compensate for this loss, amplifiers are used to amplify the attenuated signal. Let us look at an example. Here we intend to send our signal from point 1 to point 3. There is a point 2 in between point 1 and point 3. Point 1 and point 2 are connected via a transmission medium. Point 2 and point 3 are also connected via a transmission medium, but in between an amplifier is also connected. Now after we have sent the signal from point 1, when it reaches point 2, the signal loses some of its energy. Thus, it is attenuated. You can also see that the signal received at point 2 looks a bit smaller than the original signal. Now in sending the signal from point 2 to point 3, we have connected an amplifier in between. This amplifier will amplify the attenuated signal, and at the final receiving end, that is point 3, we will receive an unattenuated signal. This is how generally in communication systems attenuation is countered. Measurement of attenuation and amplification. To show the loss of energy, that is attenuation, or gain of energy, that is amplification, we use the decibel scale. Decibel scale is a logarithmic scale which uses common logarithm, that is log to the base 10. Using decibel scale, we calculate the loss or gain of any signal in this manner. dB is equals to 10 times log to the base 10 of P2 by P1, where P2 is the power of the signal at the receiving end or at the output end, and P1 is the power of the signal at the transmitting end or the input end. If the power of our signal is increased, that is, if P2 is greater than P1, then this indicates that our signal is amplified, and the dB in this case will be positive. And if the power of the signal is decreased, that is, if P2 is less than P1, then in that case our signal is attenuated and dB will be negative. If the power of our signal at the receiving end reduces to 1/2, that is P2 is equal to P1 by 2, then in this case the dB loss will be equal to minus 3 dB. Here the negative sign indicates that our signal is attenuated. Thus a loss of 3 dB, that is minus 3 dB, is equivalent to losing one half of the power. Similarly, a plus 3 dB gain indicates that our signal has gained power by twice the amount. Now, one of the reasons that engineers use the decibel scale to measure the changes in the strength of a signal is because, let's say, instead of just 2 points, our system is made up of cascaded stages, each stage having some finite gain or loss expressed in dB. Now, to calculate the overall loss or gain of the system, we can algebraically add or subtract the loss or gain of individual stages which are given in dB. Thus, the decibel scale reduces the complexity of our calculations to a great extent. In this example, our system is made up of cascaded stages. So, if we want to calculate the overall loss or gain of this system from point 1 to point 4, we can algebraically add the loss or gain of individual stages. Here, the overall gain of our system is plus 1 dB. Sometimes the decibel scale is used to measure the signal power in milliwatts. In this case, it is referred to as dBm and is calculated as dBm is equal to 10 times log to the base 10 of Pm, where Pm is the power of the signal in milliwatts. Now, if the strength of our signal is given not in terms of power but in terms of voltage of the signal, then we can calculate the dB loss or dB gain using this formula, that is dBV, that is dB when voltage is given is equal to 20 log to the base 10 of V2 by V1, where V2 is the voltage of the signal at the receiving end and V1 is the voltage of the signal at the transmitting end. We can very easily derive this formula. We know that dB when power is given is equal to 10 log to the base 10 of P2 by P1. We can rewrite P2 and P1 as V2 square by R and V1 square by R respectively, because we know that power is equal to voltage square divided by resistance. R gets cancelled and so we get 10 times log to the base 10 of V2 square by V1 square. We can rewrite this as 10 log to the base 10 of V2 by V1 the whole square. Now, according to the rule of logarithms, the power, that is 2, gets multiplied to 10. So, at last we get dBV is equals to 20 log to the base 10 of V2 by V1. Let us now learn about noise. Noise is defined as any unwanted disturbance that gets added, or we can say which gets superimposed with our original signal. There are many different types of noise. The first one is thermal noise. Thermal noise is caused because of the random motion of electrons in a wire, which creates an extra signal that was not originally sent by the transmitter. We can calculate the power of thermal noise that is generated using this formula. Np is equals to kbTB, where Np is the power of the thermal noise that is generated. Kb is Boltzmann's constant, whose value is 1.38 times 10 to the power minus 23 joule per Kelvin. T is the absolute temperature of the device measured in Kelvin. And B is the bandwidth of the circuit. Next is induced noise. Induced noise comes from sources such as motors and appliances. These devices acts as a sending antenna and the medium acts as the receiving antenna. Next is crosstalk. Crosstalk is the effect of one wire on another wire. One wire acts as the sending antenna and the other wire acts as the receiving antenna. To prevent this crosstalk issue, wires are generally twisted together in systems. Next is impulse noise. Impulse noise is a spike, that is a signal with high energy for a very short amount of time that comes from power lines, lightning, and other high power consuming appliances. Whenever we turn on any high power consuming appliances, at that time, initially for a very short amount of time, there is a passage of very high electric current through that device. This electric current is known as inrush current. Inrush current generates large amount of electromagnetic noise. This is the effect of noise, which is a random disturbance on our clean message signal. Our signal becomes noisy and corrupted. Thus, our original data is altered, and this is undesirable. Signal to noise ratio (SNR). We determine the quality of a system by measuring its SNR. SNR indicates the strength of the signal with respect to the strength of the noise in the system. SNR is the ratio of what is wanted, that is the power of the signal, to what is not wanted, that is the power of the noise. A high SNR means that the signal is less corrupted by noise. A low SNR means that the signal is vulnerable to noise and it might get easily affected or corrupted by noise. In calculating the SNR, we generally take the average power of the signal and the average power of noise because these might vary with time. As the SNR is the ratio of two powers, it is often described in decibel units. SNR dB is equal to 10 times log to the base 10 of SNR. We calculate the values of SNR and SNR dB for the noiseless channel. As the name suggests, a noiseless channel means that the power of noise is zero. We calculate SNR as SNR is equal to signal power, whatever it might be, divided by 0, which is equal to infinite. SNR dB is equal to 10 times log to the base 10 of infinite, which is also infinite. Thus, the SNR and SNR dB for a noiseless channel are both infinite. We can never achieve this ratio in real life. This is an ideal case. Some amount of noise will be present in every channel. Now let us look at an example where we compare the effect of large SNR versus small SNR. In the first case, compared to the average amplitude of noise, the average amplitude of our signal is more. Thus, the average power of our signal is greater than the average power of noise. In this case, when noise is superimposed on our signal, the noisy signal still resembles the original signal to a great extent. Thus, we can say that our original signal is not much affected by noise and the noisy signal can be then filtered to remove noise and recover our original signal very easily. Thus, our information is preserved. In the second case, compared to the average amplitude of noise, the average amplitude of our signal is less. Thus, the average power of our signal is smaller than the average power of noise. In this case, when noise is superimposed on our signal, the noisy signal is corrupted to such an extent that the original signal cannot be recovered. Thus, our information is lost. This is why it is preferable to have a high SNR. Tips to reduce noise. 1. Keep the signal wires short. 2. Cover the entire system with a metal shielding. This metal shielding acts like a Faraday's cage. A Faraday's cage is an enclosure used to block electromagnetic fields. 3. Keep the wires away from electrical machinery. 4. Use twisted pairs of wire. 5. Use differential inputs to remove noise common to both the wires. 6. Use an integrating A to D converter to reduce main frequency interference. 7. Filter the signal. Distortion. Distortion means that the signal changes its form or shape. Distortion can occur in a composite signal made of different frequencies. Each signal component has its own propagation speed through a medium and thus its own delay in arriving at the final destination. Differences in delay may create a difference in the phase if the delay is not exactly the same as the period duration. In other words, signal components at the receiver have phases different from what they had at the sender. The shape of the composite signal is therefore not the same. Let us look at an example. In this example, at the sender's side, we are sending a composite signal that is made up of these three individual components which are in phase with each other. At the receiver side, these three components are not in phase with each other, and thus the composite signal which is made using these received components at the receiver side does not look like the composite signal that we had originally sent. Thus, we can say that our signal is distorted. Distortion can also occur based on the bandwidth of the communication channel. If we are sending a composite signal and the bandwidth of the communication channel is not the same as the bandwidth of the composite signal, then the frequency components in the passband of the channel will be allowed to pass and other frequency components will be rejected or attenuated. Thus, at the receiver side, as some of the frequency components are removed, the shape of the signal will change and the signal will be distorted. We have reached the end of this video. I hope you liked this video and also learned something new. I would like to thank Professor C.D. Parmar sir, HOD ICT Department, for his thorough guidance in making this video. In making this conceptualization video, I learned many new things apart from books and explored many new resources. I'll be giving a link of all the resources in the description below. Thank you.